Well, I think we can start now. Hello, everybody. Thank you for being here with us and welcome to our webinar, Virtual and Real Labs with Daniel Erenso. This webinar is being recorded and will be available for you to watch on demand at any time. We will have some time at the end of the webinar to answer your questions, so please feel free to pop any questions in the chat at any time during the webinar. And if we don't have enough time to answer all your questions, we will reply to you by email. Before jumping into the webinar, I would like to introduce our speaker, Daniel Erenso. He's a physics professor at Middle Tennessee State University, working in both theoretical and experimental physics research. He has published more than 35 research works and presented over 60. He's also the proud recipient of more than 15 honors and awards. Welcome, and thank you so much for being with us, Daniel.
Thank you, Adhara, for giving me this opportunity. And thank you, the audiences, for taking time to attend this webinar. So what I am going to talk about is the recent book that IOP published, and the title of this book is Virtual and Real Labs for Introductory Physics 2. And as all of you know, Introductory Physics 2 covers optics, a little bit of modern physics, and electromagnetism. So first, I would start by talking about what inspired me, or what encouraged me to write this book, is the COVID-19 pandemic. So it was after spring break in 2020, which we received, all of us, from our department chair, about because of the COVID-19 pandemic, all face-to-face courses were moved to online instruction, which was started in March 23, and we were given 10 days to prepare to teach all of our undergraduates and graduate courses online. And these courses are introductory physics courses, and some of them are algebra based and the others are calculus based. And both, whether it's algebra based or calculus based, they have a lab component. So when we moved to the online classes, it was impossible to do these lab components. And because of the pandemic, although we were able to finish the spring semester, but the summer classes, all the summer classes were canceled, and we get an opportunity from the university administration to develop online classes for these courses that also provide the lab component. So that's how this started. And then after the pandemic had slowed down and we started on-ground classes, still the students, when they get tested positive to COVID-19, they are not allowed to come to class. So we need to provide them an option to do the lab component. So we are still doing that just by using what we developed in this book. So these were the main motivation for me to write the book. So the book is designed to provide the lab component for Introductory Physics 2, which can be used to teach the course remotely, on ground, or in a hybrid environment, which involves both remote and on-ground versions. And it's also designed in a very detailed way so that students can do it on their own with no instructor guidance. So the structure of the book, it has 19 chapters in optics, modern physics, and electromagnetism. And each chapter has a brief section about the basic theories that they should know before they do, whether it's the virtual or a real lab. And it's followed by the virtual lab, which begins with introductions and objectives of the lab and different parts for different virtual activities. And then it ends with the result and conclusion that the students make. And for the real lab, we have same thing, objectives and part of the real lab activities, results and conclusion. So what I'm going to do is to sample 2 chapters and show you how the virtual and the real lab works. So for the virtual labs, what we use is the University of Colorado PhET simulation, which is freely available to the public. So these are the modules for optics virtual labs. It has the bending lights, geometrical optics, and wave interference. And the other is for the modern physics lab, which includes black body spectrum, beta alpha decay, atomic physics lab, and photoelectric effect lab. And for the electromagnetism part, we use their circuit kit for DC and also AC and Faraday's law about magnets and also Coulomb's law. So all these simulations are freely available at the University of Colorado Boulder, freely for the public. So as for the real labs, primarily we use the Pasco modular circuit basic kits that you probably be able to see it here. I have brought sample, and also for the optics lab, we use the optics lab kit from Pasco. So as I said, I'm going to sample 2 chapters. One is from optics, the first chapter, which is about the law of reflection and refraction. And the second chapter, the second sample that I'm going to consider is chapter 11, which is constant electric current circuits from electromagnetism. So we begin with chapter 1, the law of reflection and refraction. So as I said, each chapter starts with basic theory. So for example, for chapter 1, we talk about law of reflection and refraction. So they see a light coming from one medium going into another medium. They need to know how the reflected ray and the incident ray are related, and how the transmitted ray and the incident ray are related. So the theory that explains these relationships are the law of reflection, the law of refraction, and also there is what we call a total internal reflection and critical angle. So in the law of reflection, the angle of incidence that you see here must be equal to the angle of reflection. And this is Snell's law or law of refraction, which relates the refractive index of the incident medium, the angle of incidence the refractive index of the transmitting medium and the angle of transmission. So the other thing is when light goes from high refractive index media to low refractive index media, it can go through total internal reflection if we crosses the critical angle. So these are the basic theories. It's brief. So they read this basic theory, and then if it is a remote class, they are going to use a virtual lab. So the virtual lab, it has a list of objectives. So the first objective is to understand the laws of reflection and refraction of light in a better way. And the second objective is using the law of refraction, they need to find out the index of refraction of glass. And the third one is they need to understand what happens when light goes from one medium to another, from a denser medium, which means high refractive index, to low refractive index, what happens, and vice versa. And the last objective is to study total internal reflection and critical angle. So to achieve these goals, they are directed to go to the University of Colorado PhET simulation. So they can click the link that's provided in the book, or they can copy this and paste it into their product. So when they click that, it takes them to the PhET simulation bending light module. So there is a list of instructions that takes them step by step what to do. So they open this module and then follow the instructions. So the first part is to verify the law of reflection, which states angle of incidence equals to angle of reflection. So to accomplish this objective, they follow a list of instructions. So first, they need to turn the laser on by clicking the red button, which direction the transmitted light bends away or towards the normal. They need to answer that, and they need to explain why. So just to show you, so when they click that, that's what they see. So the instruction tells them to click that. So they see the incident light partly reflected, partly transmitted. So in this case, it bends toward the normal. So they need to answer these questions. Sorry. So that's what they see. And in the book, if they cannot figure out these on their own, and if there is a figure that's provided to make it clear for them, and they need to answer the questions that's here asked in the space provided in the book, and then they are instructed to drag the protractor from the bottom left corner and set the incident angle to 0. So according to the instruction, they put the protractor at the center and they set the angle of incidence to 0. And there is a question, what can we say about the angle of reflection when the angle of incidence equals to 0? So they need to answer that. And then they are instructed to increase the incidence angle by 10 degrees, measure the corresponding angle of reflection, and also at the same time for later data analysis, when we get into law of refraction, they need to measure also the transmission angle. And they record the values on a table that's provided to them. So according to the instruction here, they increase it by 10 degrees. So it shows them what they are going to expect. So this is when they increase the angle by 10 degrees, they see the reflected ray, and they see the transmitted ray. So from the protractor, they read this angle, and this angle. And then they fill their result, their measurement for angle of reflection on this column and angle of transmission on this column for this list of angles. So since later we are going to do a linear analysis for the law of refraction, they need to calculate the sine of each of these angles, the incidence and the transmission. So then they are asked questions here. So according to the law of reflection, they expect angle of incidence to be equals to angle of reflection. So if they were to plot this, what would they predict for the graph slope for the vertical intercept? If that's not clear to them, then they read this, which tells them about a linear relationship between two quantities, y and x. And then they need to provide their answer in the space provided. Then they start to make a graph of the reflection angle versus incident angle. And they are asked to do this using Excel. And using Excel, they need to determine the equation for the linear graph that they see. And from that linear equation, they need to figure out what's the slope, what the vertical intercept here. And they don't need to do this on the graphing page. Once they made this analysis on Excel, what they need to do is just what they need to sketch what they observed or what they see on Excel graph. So, but they are required to properly label the axes, and they need to have a title for their graph. So the second part is to study law of refraction. By applying law of refraction, they intend to find the refractive index of glass. So they have already done the measurement. So what they are going to do is next is to analyze the measured angle of transmission versus angle of incidence. So according to the law of refraction or Snell's law, that's the relationship. And obviously this is not a linear relationship. So from this nonlinear data, they need to make a linear data so that they can analyze their data graphically. So by comparing this equation with the equation for a linear graph, they are asked to find what should be y. So in this case, it should be sine of theta t. What should be x? That should be sine of theta I. And m, it's the slope of the linear graph is related to the refractive indices of the two media. And obviously, when they compare these two equations, they expect the intercept should be close to 0. So they need to answer this also in the space provided here. Then they make a linear graph using Excel. And from this linear graph, they are asked to find the equation for the linear graph. And they provide that on the space provided. And then whatever graph they see, they need to make a sketch in their lab report, which is actually the book. And it's easy to do this in the ebook version. They can use Adobe to edit, type everything, what they measured, what they recorded. Then the next step is using the linear equation slope. They need to figure out what is the refractive index of glass. And they show their work again on the space provided. Then they need to see what they measured experimentally by making a linear graph analysis, how it compares to the actual value. So they need to calculate the percent difference between the actual value and the experimental value. And again, they need to show their work. So the last part is a total internal reflection. So in order to see a total internal reflection, the light should go from a medium that had a higher refractive index to a medium that had a lower refractive index. So they are asked to set, using the simulation, they are asked to set the incident medium glass and the transmitting medium water. So they can do that on the simulation. So what they expect is this. So that's glass, that's water. And there is a question here. Which direction does the transmitted light bend? They need to answer that. Away or toward the normal. And then first they make a prediction for the critical angle before they try to observe it experimentally using the simulation. So as I showed in the basic theory section, there is a relation that shows how the critical angle is related to the refractive index of the incident and transmitting medium. So based on that, they make a prediction. After they made the prediction, then they try to find this critical angle by gradually increasing the angle of incidence by rotating the laser in a counterclockwise direction. So in the process, they must observe that when the angle of incidence is greater than the critical angle, there is no light going to be transmitted into the water. So what you see here is just when they rotate from 45-degree, when they increase, so that's what they see. And then when they pass the critical angle, they see the light is totally reflected. So they should estimate from these two, here is about 62, and here it has passed, and we have a total internal reflection. So they would be able to estimate the critical angle when they just move this one back and forth. Now, there is a question to make sure that they have really understood what's total internal reflection and when total internal reflection happens. So the question is, suppose we change the incident medium to water and the transmitting medium to glass. So if we reverse it, and if we try to repeat the step that's discussed in 3, do we observe total internal reflection? The answer is no, and they should explain that. Just this allows them to really, allows us to really make sure they understood what they were doing. And finally, after all this, after they achieve all this objective, then they need to make a brief overview what is accomplished and concluded in this virtual activity. So that's how the virtual and also the real lab ends for each chapter. So next, what I'm going to show you is the real lab that we use using Pascal's optics kit. So the objective is exactly the same. What changes is what they accomplished in a virtual lab, repeated in a real lab. So if students, they cannot make it to class, they do the virtual lab, which is pretty much a replication of the real lab. So these are the supplies they need: array table, a slit mask, a cylindrical lens, and a mirror with curved and plain sides. So again, as we did in the virtual part, the first part is to verify the law of reflection. And we use a plane mirror here. So they are instructed to affix the ray table, the slit plate, and turn the light on. The slit plate has 7 slits. So align the light passing through the center slit with the 0 mark on the ray table. So following this, they are trying to do they are encouraged to do on their own without referring to the figure. If that's something they can do it, then they can refer to the figure that's provided in the book. So that's the light source, that's the slit, and this is the ray table. And as you can see, the light passing through the center slit is lined up with this, with the 0 mark. And then they need to affix the slit mask to block the other rays except one. And they need to make sure the ray is further away so that we have parallel rays. If it is close to the source, it's not going to be parallel. So they need to make sure that, and then place the ray optics mirror at the center of the ray table. That's the plane mirror with the plane reflecting surface facing the light. So if they can't do that, then again, they will be provided with the figure. So that's the plane side of the mirror. This is just only one ray, the central ray. And then they need to rotate the ray table with an increment of 10 degrees up to 80 degrees. And they record both the angle of incidence and angle of reflection. So just if they can't figure out that, in case, this is when, for example, when the ray table is rotated by a 10 degree. So they measure, they read this angle, they read this angle. So that's the angle of incidence, that's the angle of reflection. And then they record the values in the first and second column. So the third column is for the second part, which is about the law of refraction. Then they asked the same questions that we asked in the virtual lab. So according to the law of reflection, angle of incidence must be equal to angle of reflection. So if they were to plot this theta r versus theta I, what kind of graph they get? Is it linear or non-linear? So they need to figure out that. And also the same thing what we did in the virtual lab, they need to make a graph for theta r versus theta I using Excel, and do the slope and the equations intercept determined from Excel agree with what they predicted here. And on the graph paper, just like they did it in the virtual part, they make a sketch of the linear graph they obtained using Excel. And then the next step is to analyze the data that they collected to study law of refraction. So to that end, they replaced the ray optics mirror with the D-shaped glass, but they keep everything else the same. So they use the rate table, the slits, the mask, and everything when they studied the law of reflection with the plane mirror. So everything there is going to be the same, only they replace the plane mirror with D-shaped glass, which is the cylindrical lens, and they the lens according to this instruction. And if that's not clear to them, figure is provided. So that is the cylindrical lens with the plane side of the cylinder lens with the radial diameter. So that's the plane side, and it's aligned with the diameter of the radial. And so this is at 90 degree relative to this surface. And then they are asked to increase the angle of incidence by 10 degree, just like they did it in the virtual lab, up to 80 degree. And they need to record the angle of transmission and also the angle of incidence. So if that's not clear, also a figure is provided. For example, here is when it is rotated by 10 degree. So that's going to be the angle of incidence, and that's going to be the angle of transmission. Then they need to know also, when they do optics lab, they need to know how to make ray diagrams. So they have to make a ray diagram for that shows, the cylindrical lens and the normal to this surface and the incident and transmitted ray. And they need to label also the corresponding angles of incidence and angle of transmission. So now they have recorded both the angle of incidence and angle of transmission. So they are going to analyze the data that they recorded. So again, they are asked to make an Excel graph for theta t versus theta I, the transmission angle versus the incidence angle. And they need to make a sketch of what they see on Excel for theta t versus theta I. What's the difference between theta r versus theta I? They should have gotten for theta r versus theta I a linear graph. And what's the difference? So this is obviously is going to be linear, whereas this one is linear. And then they proceed to analyze the measurement they took for the angle of incidence and transmission. And the objective is to apply Snell's law and find the refractive index of glass. So they need to make a linear data out of the non-linear data, theta t and theta I. So just like we talked about in this virtual lab, they need to figure out what should be y, what should be x, what's the relationship of the slope of the linear graph with the refractive indices. So they need to do that. And then again, they make a linear graph, and from the linear graph, they need to find the equation, and from the equation, they need to figure out what's the slope value, and using the slope value, they must find the refractive index of glass. So this is a real experimental result. Obviously, there is some real experimental uncertainties, so they need to find the percent difference between the actual value of refractive index of glass and their experimental value. Then after they figured out the refractive index of glass, the next phase is to study total internal reflection. and determine the critical angle for total internal reflection. So they follow the instruction. We follow, the same procedure pretty much, except that we flip the cylindrical lens. So they flip the cylindrical lens. Earlier the plane side was facing the light. Now the curved side is facing the light. So that would allow them to analyze the light coming from glass to air. So from high refractive index to low refractive index. So they rotate the ray table with an increment of 5 degrees until they reach to the critical angle where they begin to see all the light totally reflected. And they record the angle of incidence and the corresponding angle of transmission until they reach to the critical angle. So that is when, for example, it's rotated by 10 degrees. So that's gonna be the angle of incidence for the light going from glass to air, and that's gonna be the angle of transmission. So just by rotating this, eventually they would be able to see that there is no transmitted light here. Everything is gonna be reflected. So the goal is to find that angle. But before they do the experiment, they are asked to make a prediction. So they predict the critical angle by using the refractive index they determined experimentally and the refractive index of air, which is 1. So they make that prediction before they determine it experimentally. So by just rotating the table, they need to collect a few data for them to graph for the transmission light versus incident, the transmission, the angle of transmission versus angle of incidence. So again, they do a graph for theta t versus theta I. They get a nonlinear graph, and they need to sketch this graph and the two graphs they already have for the reflected versus incidence, transmission versus incidence, and they see a distinct difference between these three graphs. And from these three graphs, they need to discuss what the similarities and differences. And there is a question here also. By fetching the two sides, the plane and curved of the cylindrical lens, they have studied the refraction of light from air into glass and from glass into air. So in the sketch they make here, they must have seen one linear and two nonlinear graphs, and they label each of the nonlinear graphs as air to glass or glass to air, and they need to explain how they knew that just by looking at the graph. Then the final part is just like the virtual lab. They briefly discuss what they have accomplished and what they have concluded from this real lab activity. So that is chapter 1. So the other chapter that I'm going to sample for you is chapter 11, which is about constant current circuits, DC circuits, and I selected a relatively simple one, which is resistors connected in series and resistors connected in parallel. So like every chapter, for each chapter, the first section is basic theory. So all they need here is, how they relate the potential difference across a resistor to the current and the resistance, and also how they calculate the equivalent resistance when two resistors are in series and when two resistors are in parallel. And what's the same when they are in parallel combination, when they are in series combination? The current is the same, here the potential difference is the same. And also, how do we calculate the power supplied by the battery? We need to know the potential difference across the battery. We need to know the source current, or how to find the power lost in a resistor, whether it's in series or in parallel. So that is related to the current square and the resistance. So these are the basic theories that they should know before they start the real or virtual lab. So again, we start with the virtual lab if that's what they need to do, if they cannot come to class. So they do this virtual lab, which is the replication of the real lab. So the objectives. The objective is to practice how to build an electrical circuits with two resistors that are connected in series or in parallel. And second objective, how to find equivalent resistance for resistors connected in series or in parallel. And third objective, to get more experience in measuring current, voltage using an ammeter and a voltmeter when resistors are connected in series or in parallel. And the last objective is to explore the relationship between power supplied by the battery and the total power lost in a resistor. So the virtual lab directs them where to go to do the simulation. So they can again click that. It takes them to a DC circuit lab. So when they click that, it takes them the list of things that they need to build a circuit. So the first part is using a battery, a switch, and two resistors. They need to build this circuit. So all they need is just follow the instruction. So they take a wire, they take a battery, they need a resistor, another resistor, and they connect them according to the instruction. So I'm not going to take time building this one, but it's easy. Students, they like it. Just keep on clicking back. Sorry about that. It just takes me back. All right, so then they build the circuit, and then they need to set the source voltage to 5 volt and the resistance, one resistor to 47 ohm, the second to 100 ohm. So this, you can change this, but the real lab, in the real lab, we use these resistors. So I just want to make, the virtual lab to be a replication of the real lab. So that's why we selected these values. And they can click on each of these elements to set the required resistance or the required voltage. And then there is a question, are these resistors in series or parallel? Is it the current or the voltage that's the same for these two resistors? And they need to find the equivalent resistance. And then they make a theoretical prediction for the source current and the current through each resistors and the potential across each resistors, and they record the values in this column. The second column is for the experimental value. And then they are asked to turn the switch on, check the boxes for conventional. You know, in the previous, so if I go back here, so what you see here in the simulation is the movement of the real charge carriers, which are the electrons. But by convention, you know, it's the positive charge that carries the current. So they need to select conventional to show, to see the conventional current direction. So when they select that, they can see that, you know, the current is moving in a clockwise direction. And now they need to use an ammeter to measure the current and a voltmeter to measure the potential across each resistor. So they need to know how to connect the ammeter, how to connect the voltmeter to the circuit to measure these two quantities. And they record the values that they measured for the current and the potential difference in this column. And if they can't figure out that, a figure is provided to them how to connect a voltmeter across the resistor or an ammeter to measure the current they need to break the circuit. And then by using the theoretical and experimental results for the current and the potential difference, they are asked to find the theoretical value for the power supplied by the source, the power lost in resistor 1, in resistor 2, and similarly the experimental value. And then they need to know what the relationship between the power supplied by the source and the total power lost in the resistor. And they use measured values for the potential difference to make an electrical potential versus path graph. And they are asked if all the measured currents and voltage agree with the theoretical values that they predicted. If not, they need to identify which values didn't agree, and they need to explain what causes the disagreement. So the second part is resistors that are connected in parallel. So they use the same resistors and they set the same source voltage, and they build this circuit, and they need to figure out, they are not told it's they need to know what kind of circuit they build here. Are they in series or in parallel? And they need to make, just like they did it in resistors in series, they need to make a prediction for the theoretical source current, the current through each resistor, and the potential across each resistor. And they need to integrate the ammeter to the circuit and connect the voltmeter to measure the source current, the current through each resistor, and the potential difference through each resistor. And they record the values in the second column here. So if they can't figure out that, so for example, to measure the source current, that's how they need to connect the ammeter, and that's how they measure the voltage across each resistor. So using the results, then they need to calculate, the theoretical and experimental values for the source power, the power through each resistor, and they need to answer the same questions that were asked in the series connection. And finally, they need to write a brief statement about the accomplishment from this activity and also the conclusion. So then they go to the real lab. If students are in class, they are required to do only the real lab. They are not required to do both. It's just if they cannot make it to class, they do the virtual lab. If they are in the lab, and they should do the real lab. So it's the same objective, and we use the Pasco modular circuit basic kit that you see here, and it's like a Lego. So these are all they need, and before they build the circuit, they need to measure the resistance of the two resistors, which is labeled as 33 and 100 ohm. But when you measure it, they don't get always this exact value, so they need to use the measured value. So they do that, and so this is the same circuit that they need to build, and we use the battery here, 2 batteries, each 1.5 volt, and they need to measure also the voltage across the 2 batteries in the circuit. And for the circuits that's shown here, first they need to make a theoretical prediction for the source current, the currents through, and the voltage across each of these 2 resistors, just like they did in the virtual lab when the switch is on. So they need to turn the switch on, otherwise this is going to be open and the resistance is going to be infinity. So they make these predictions and they record it in this column, and then now they are asked to construct the circuit that they see here. So if they can't do it, there is a figure that shows them how to construct the circuits from the modules. These are the batteries. These are the 2 resistors that are connected in series, and this shows them how to hook up a voltmeter, for example, to measure the source voltage here. And there is a switch here. Initially they need to keep the switch off, but when they are ready to take a measurement, they turn the switch on, and they use the multimeter to measure the voltage across the batteries and show that the total voltage is 0 across the batteries and across R1 and R2. And they need to turn the switch off and integrate the ammeter. So somewhere here they need to break the circuit and they need to put the ammeter. And if they don't know how to do that, a figure is provided here to show them where to put the ammeter. And they need to know what the difference between connecting a voltmeter and an ammeter to an electrical circuit. So they need to provide an answer for that. And so this is for parallel connection. So for the circuit that they see here, when the switch is on, they need to make a prediction for the theoretical values for the source current, the current through each resistor, just like they did it for a series connection. And then they record the theoretical value, and they carry out the experimental measurements by building the circuit. And if they can't build it on their own, or if they want to check what they build, then a real circuit that's built is given to them. And again, they integrate the ammeter, the multimeter, and they take the measurement. So I'm kind of running out of time. So if they cannot do it on their own, for example, if they want to measure their currents through this resistor, they need to take out this block, and they need to integrate the ammeter there. And based on the results for the theoretical and experimental values, they need to establish what the relationship between these three currents. So that's sort of asking them Kirchhoff's current law. And finally, they do the result and conclusion part. So first they need to tell whether what they measured and what they predicted, if they agree, and if there is a disagreement, why the disagreement, and then they write a brief overview what they have accomplished and concluded in this lab. So these are the two samples that I selected. As I said, there are about 19 chapters, pretty much more than 95% all have a virtual and a real component, except a few, and they use predominantly the virtual labs use the PhET simulation, which is available at University of Colorado, Boulder, and it's free, and anybody can access it, and it's available in many different languages. So in conclusion, what I am going to do this summer is, here in America, at least in my state, I know that students often take introductory physics, both algebra-based or calculus-based, in schools close to their home during the summer. So we always give this course every summer, and there is a high interest of people taking this course online asynchronously. And I have been teaching this introductory physics to the algebra based since 2003. And I have seen a lot of students have such kind of interest. So in this, in the summer 2023, I have planned to create 3 sections as synchronous, and on the ground. So students, whichever suits for them, they can take this course. And I'm going to use these virtual and real labs, and it covers all these 3 topics. And as a text, this book is just only for the lab part. The students, they need to have the textbook for the lecture part, and this is right now is the textbook that we use in our school, and it has online homework assignments, online reading quiz, and which is integrated to our online system. So it's gonna be it's not going to be hard to create these asynchronous online courses. So with that, I would like to thank you, and feel free to ask if you have any kind of questions. Thank you.
Thank you so much, Professor Erenso. We have some questions. So firstly, somebody said, great talk. And thank you so much for the
Thank you.
presentation. They would like to know if the book has a manual solution in order to help newcomer teachers.
Manual solution?
Yes.
No, it doesn't have solutions because it's just a sort of instructions where everybody, even students on their own, they can do it. Just they follow the instruction and do the activities, and their result tells them what they have measured or what they have predicted, if it is right or wrong. There is a theoretical prediction and experimental measurement. If these two don't agree, then there is something that they do wrong, and they are required to figure it out on their own.
Cool, thank you. Are you working in another book like mechanics, Newton law, etc.?
Yeah, well, the plan when the pandemic strikes, my plan was to develop both the first part of introductory physics, which is primarily mechanics, and I finally, decided just only to focus on this one to make a really good product instead of just rushing it. But depending on the needs of this book, I might resume working on that, because I already have the simulations for the mechanics part. It's not fully developed, but the virtual labs for the mechanics part, it's not fully developed, but depending on the need of this book, I can pursue, I can continue working on that.
Thank you. Somebody is asking for a direct URL web address for the free service that you have sampled. So maybe we can send a follow-up email with the direct link for the attendees to access it.
So this video?
The link of the
virtual lab?
No, the simulation that you have used for from the Colorado University.
Yeah, so it's they can access. If I go back here, in the book. So let me open the book. So this is the book, the ebook. So each chapter, when it comes to the virtual lab, there is a link that takes them to that site. If they have the copy of the book, it takes them to the site.
Brilliant. Yeah, that also links very well with our last question. Somebody asked where can they find the copy of the book. If you go to IOP Science on our portal, you would be able to download the book for free for a limited amount of time until mid-October, and you will be able to enjoy it forever. In there, as Professor Erenso was mentioning, you will have links for this program and all the details that he has talked to us today. So I'm afraid we have run out of time. We are a little bit over the hour. So I want to thank Professor Erenso for being with us. Thank you so much for a very informative presentation. And thank you so much, everybody, for attending. You will receive a follow-up email with a link for you to watch on demand this webinar at any time. So thank you so much, everybody, and have a nice day.
Thank you.